day 16 of Advent of Code. I'm getting kind of a late start. I'm going to send a Twitter note out just in case anybody wants to join. I was out for dinner with my coworkers, so happy Advent to all, Merry Christmas, and so forth. So let me, working with a little different setup here. So I'm gonna switch the screen share. And let's look at today's problem. Oh, I did manage to get both stars for yesterday, so let me start with that. So it took me about 3 hours, and I did not solve last night. When I had left it, I had not tested my solution yet or finished all the parts of it. So turns out I did have a bug in the heap merge function. A small one. I had swapped the two A and B cases. And then the other things were fairly straightforward. I needed a function to update the matrix, so I did that in functional form. It takes a matrix and a position and a new value and updates that. And the only interesting thing here is I had to work kind of hard to convince it that the when everything was pasted back together, it was the correct size. Um, sorry. And so once I'd written that, then we could fill in the functions that I had written the types of but left unimplemented yesterday. So update neighbors to go to each of the neighbors and say, implement the Dijkstra step of say, well, your distance is no worse than the distance to me plus the cost to get to you. And if it's infinity, then that's, we always update you, and if it's finite, we only update the neighbor cost if it's lower. And then here's the code to insert those neighbors onto the priority queue. And here, we sort of run into this dumb thing where I had used inconsistent orderings in the tuple and had to reverse them. But the type checking catches when I miss that. And then, finish node was just a simple call to update. So when you put all those together, here's our Dijkstra's algorithm. And this was all written yesterday. We pop something, the minimum value of the priority queue. We look at its what value it's in. If it's finished, then we don't do anything. Otherwise, it's some finite value. We finish it. We update the neighbors. We insert the neighbors into the priority queue. The interesting thing for part 2 is that this function, which is just a map over the indices, is very irregular in how much time it takes f star to verify it. And sometimes it times out. So I bumped it up to like 60 seconds. But sometimes it would verify in a couple seconds, and sometimes it would time out and say I can't type check this. I think it's probably due to all the integer math here we do in every step and verifying that everything remains in bounds even though we do that. So yeah, I was able to finish both parts of yesterday's problem, and so let's take a look at the problem from today, which dropped an hour ago. Okay. Bits transmission contains a packet. Might have a few 0 bits at the end. Okay. Packet. Every packet starts 3 bits, then code the version, 3 bits, then code the type ID, and they are most significant bit first. Packets with type ID 4 are a literal value. The binary is padded until its length is a multiple of 4 bits and is broken into groups of 4 bits. Each group is prefixed by 1 bit except for the last. I'm having flashbacks to MPEG encoding here and all sorts of funny bit manipulations. Okay, any other type of packet, any packet with a type ID other than 4 represents an operator that performs some calculation. Hello. Welcome. So I'm trying to solve today's Advent of Code problem in F star. Okay. To indicate which subsequent binary data subpackets can use one of 2 different modes. Okay. The length type ID is 0, then the next 15 bits are a number that represents the total length in bits. Okay, and if the length ID type is 1, number of subpackets. All right, this seems like it's gonna be complicated. All right, so our first task is add up all the version numbers. All right, let's get started. I will open up a new file for today. Which I didn't do yet. My apologies. Kind of boring to see me. Oop. Yeah, so I can't follow chat as well today because I don't have my second monitor up. I will have that running in the background until I remember to check. It's not import. I fall back. It's interesting which language I fall back to while doing F star. Sometimes I try to write Python. More rarely I try to write Go. all printf. All right, so let's define the data type as an ADT. So the message is either a literal, is this the right way to think about it? It's a version type ID. Sure. Okay, so we've got a version, that's a natural number, and so fstar actually has a library called miniparse that outputs verified parsers, which seems like it would be great for this, but I can't understand how it works or how to use it, or whether it can be extracted to something I can actually run. It must do it somehow, but there's unfortunately not a lot of documentation to go with the implementation. But it's kind of cool. You give it a schema and it outputs a parser for that, which is just what we need. But you know, I can, so in the examples directory, it's mini parse. It's got all these examples. It's like I don't know what any of this means or how to run it. So there is a make file. But I think it extracts to C instead of to OCaml like I've been doing. And I haven't experimented with that at all. So I'm not gonna try to get that working on stream, even though it might be the most idiomatic way to go about this. Okay, so a message has a version, a literal has a version, and packet ID, which is literal, and then a value. And the other thing it can be is an operator. And I think in part 2 we'll be going through this separately. We'll be expanding the operator to a bunch of specific operations based on the type code. But for now, all we know is that it's got a list of messages. So operands. All right, so let's type check that and make sure I haven't made a silly syntax error yet. All right, it's good. Okay, that's yesterday's input. Let's look at today's input. So you know what? I'm just gonna skip the file input. And we'll just include it inline in our code. And we can do that with the other examples later. FSTAR does not, as far as I know, have a multi-line input, so that's just one big line in the source code, but that should be fine. All right, so we need to convert this to binary. 4 characters at a time. So hex to binary. So let's I'm wondering how I'm going to represent binary. So should we represent it as bools? Should we represent it as natural numbers 0 and 1? Should we just define a bool type, a bit type? You know, so we could do. There's new type. All right. There we go. So this will be a list of bits. And I'm not going to write the nice tail recursive version. We'll just recurse on. Oh, we have to convert this to a list of characters anyway. Yeah, we'll do it like this. So whenever we're cursing on a list, we write the same code, match L with if it's an empty list of characters, then it's an empty list of bits. Otherwise, we append that first character with, we need to mark this as recursive. Binary of the tail. Okay, and so given a character, we're going to return a list of bits, and we could do this in various clever ways, but I'm just going to do the simple, straightforward thing of match the individual digits. So that's how we do a string literal, a list literal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right, I should get smarter here. Oh. There's probably some cool Emacs command to just do this automatically, but I don't know what it is. Yeah, I probably could have done this smarter. All right, here's what I'm going to do. Okay, now. All right, that looks like the right table. And so because we matched on characters and we didn't tell it that this was a list of characters that only contain these characters, we'll just do a catch-all. If we don't do that, if you haven't seen F star before, oops, it will actually warn us that, hey, their patterns are incomplete. We couldn't prove that those were all the cases that exists. So if there's anything left over, we'll just so the problem with so we could do that, but this would cease to be a total function. So by default, the value is uh, tot, which are functions that always terminate and run to completion and don't throw in errors. So we could put in another effect here. That's the name of that annotation. But since we can eyeball it, and Eric doesn't play games with us, it's okay to do that. But we could certainly, uh, you know, one option we could do is to return the optional type and say, uh, it's either going to be some list if it's valid, or it's going to be none if it's an error. And that's something I've done in some of the other days. You can find that. This function, because I just want to. The problem is I want to append here. I don't want to spend a lot of time futzing with it. Well, if it's none, then don't append, and if it is, then do. So we'll take advantage of our domain knowledge here. All right. So, oops, that's not. All right. We could go back and actually validate the input more, but we're doing enough input validation on the bits as it is that I feel like we got enough work ahead of us. All right. So this, let me just check order. Yeah, we're gonna put the first bits first. So I've written a parser combinator, but it was one that worked on strings. And one of the things I noticed is that it was very difficult uh, to convince F star that a function will terminate. So functions that are total always have to terminate. And if they're recursive, we have to be able to prove that they terminate. So the default way F star picks that is it just takes the lexicographic order of its arguments. Here we only got one argument, and say, well, every call has to be less than in some order. So the list has to get shorter for this to terminate. And that's exactly what it does here. So we didn't need to do anything special. But if we write a recursive descent parser, then we run smack dab into this problem. So let's try this and see how far we get. So parse not string, parse what was the name we were given? Oh, bits. Okay. All right, what we want to do is parse a packet. Okay. And so what we need as return value is how many not just what did we find, but how many bits are left. because that's where the next packet is going to start. So let's return a pair of a message and the remaining list of bits. Okay, so and here I feel like it would be a better idea to have an error. So let's oops, can't use capital letters. That's one of the things about F star is capital letters are reserved for type constructors or effects, but not ordinary types. So can't use camel case. You have to use snake case or camel case with initial small letter. All right. So if it's okay, then we get a message. I'm gonna M should be fine, and rest the message, which is the list of bits, or we get an error, and we'll represent those by strings. All right, so there are two type constructors for a parse result. So the first thing is, okay, so this will be a parse result. So if the length of the input is less than what's the minimum we need? We need at least version and type ID. Sure, let's start there. Okay, so I think we don't have in list a sublist command. I think I had to write that. So let me find that in my mini library. Okay. So there's a definition of sublist. I'll copy that. I don't know if I need any of these lemmas. Like the one that I spent a lot of time writing here is that the sublist of a sublist is itself a sublist. Let's see how far we get. All right, so we got a couple of things that are parameterized by type, so we can use them with any list type. This first one just takes the first n elements, and this takes starting at I, and it says taking j, but that's taking n elements. And so that is annotated. The types are annotated. So this is a list that has to be long enough that these indices are valuable, are okay. And it returns a length list that has the length that we asked for. And what is, oh, okay. So the problem here is string has its own, the string module has its own length argument. And so we'll import the one from the list library rather than rewriting all these to be the qualified name. When we have to reload, it sometimes get cranky about syntax errors that it didn't before. Okay. So the version is the sublist of the input well, sure, we'll use sublist. From 0, we take 3 characters input, and the code, is that what it was called? Type ID, all right. Okay, so we're gonna match on the type ID. So we should probably convert these back to decimal. That's how we define these. So let's I'm wondering whether we're gonna wanna, well, first I'm wondering whether there's a right way to do it, but the second thing I'm wondering is if we're going to want to know how large the integer is at some point. But, all right. So we're going to take a list of bits, so this converts most. Can we do it this way? We're going to have to switch things around. So let's see. If we've got phooey. All right, so previous number. All right, so if we reach the end of our bits, then the value is just the last number we calculated. If we have a 1 bit and the rest of them, then it's going to be okay, we have to, we can't use star. Well, we could use star, but we have to open another package that specifically defines it. By default, star is reserved for creating pair types, the Cartesian product rather than the number product. Okay. So that's our new value. So we won't bin to netbox of the rest of the input. Our new number is 2 times the previous, shift everything up by 1 spot, plus 1. And if it's 0, then we just multiply. Now, it would be nice if we could sort of write a proof that this worked. To do that, we'd have to have some model, which is unfortunately about as complicated as this. So one of the things we could do is write the natural number to binary function and prove they were inverses of each other. I'm going to take a shortcut here and just write some test cases instead of doing that full proof. So we're going to assert that bind to nat of 1, 0, 1, starting with 0. Oh, need to use assert norm rather than just assert. So that should be 5. Okay, so assert gives something to the solver that F star uses as a backend. And this, by default, that's only unrolls recursive loops a small number of times. And assert norm says normalize the expression as much as you can by evaluating it until you and then give it to the solver. So it might or might not work with assert. Let's try it, but it does work with assert. But if the list is long enough, that would stop working. Okay, so all right, sorry, let's finish writing. Writing this up into nat auxiliary input starting at 0. All right. I used the that's not right. We want 0 characters. All right, so we match the type ID, and if it's 4, then we're going to parse a literal. Starting at all right. Do we have the okay? We don't have the opposite of first n. We want everything after n. Which we could do here. Sure. Let's. The problem is we lose some information here, and that might cause us problems if we're going to recurse, that it won't know that we're calling it with a shorter input each time. Okay, we can fix this. So let's say we have to skip at least 1 character. And then we're going to guarantee that the length of x is less than the length of our input L. So that'll, anybody who uses this function will get that lesser guarantee. It's not as precise as knowing exactly what the length is, but it knows it's shorter. And so as long as we're making the input shorter each time by at least one character, then we'll eventually terminate. So we should be able to just define this in terms of sublist skip length of L minus skip of L. One too many parentheses. Okay, and it verified that when we call sublist like we do, then that property we specified is satisfied. Is satisfied. Okay, so we're going to parse the literal and we're going to give it the suffix after the first 6 bits. And otherwise, we're going to parse an operator. Okay, let's give it the version. What did we specify here? So we didn't save this type ID. We're probably are going to need that for part 2, but let's leave it be. We just need the version. Yeah. Okay. All right. So since these are mutually recursive functions, we're going to have to define them all together in one big let rec clause. So parse literal. I'll just leave that a placeholder for now. And parse operator. Oh, I didn't specify. Oh, I did. I didn't. I didn't give it the what it's the suffix of. Sorry, my Emacs autocomplete has gotten a little wonky here. I don't know why. There we go. So F star queries functions by default. All right, so this was what I was worried about. It says it can't prove that this call terminates. All right, let's make it a little more explicit. So what we say is each time we decrease the length of the input. I may need to look up how to do this. Okay, That worked. We just had to specify it everywhere. It probably would have worked if we'd put version second. Then the default rule would have worked. But okay. So if we have a literal, then we've got these funny rules about that they're 5-bit sequences. And the first bit in each one says whether it's the last group or not. So we'll have more clauses here. All right, so I guess we could do it all in parse literal. Right, so it either starts with the 1, in which case we take 4 bits and then append them to this doesn't work because we got a parse result here. All right, so let's write a parser that does this. It doesn't need to be part of this letrec because it doesn't. So parse integer. All right, what I'm going to do is I'm going to go fix parse result so it takes a type. So we can use it for both full messages and other things we parse. So this is, we just need a name value. Oh, this is not going to work. Okay, so we need to take, the constructors need to take the type as an implicit first argument. So the pound means it's an implicit argument. Not the hash sign. The octothorpe. To the argument to function. Okay. I've been getting this wrong for quite some time now. No. All right. Let me look at how I did it yesterday. Which had a much more complicated example. Oh, and it needs to be capital T type. I'm very confused at too many arguments. Okay, that looks okay. Is this line actually okay, or are they? No, it's the same problem to me. Okay. Uh, it's an implicit argument, so if we supply it, it has to be with the hash. Okay, I don't get why it can't. All right, what it's complaining about is because it's a parameterized type. It can't decide whether this type has equality, or it can't implement equality for this type, which is strange because I specified that the parameter was in equal type, so it should have been okay. But we'll just say, okay, fine, you can't do equality on this parser result. Okay, so this is going to be a parse result that returns a message. This will be a parse result message. This will be a parse result message. But this is a parse result integer. So um, let's do this in two parts. We'll just parse I need a name for okay. Okay, so if the length of the input is less than 5, that's an error. Okay, else if if the first, well, let's just match it. Okay, so if it's true, oops, we used 1 and 0. True and false mean something already. Then make the recursive call. So we do the suffix after 5 bits of the input. And this call would error out if we hadn't done the length check. Sublist the four subsequent bits. We can simplify it. I was going to say we'd simplify this, but not with the parse result. It's fine. List bit. I make this mistake a lot. Okay, this needs to be recursive. All right, I think I made a mistake here. When we use the type name, it should be explicit, but when we use the constructors, then it'll be implicit. So, all right, so this is going to be okay, and here's our value, and here's the remaining bits. All right, and again, to prove recursion, we have to say this decreases the length of the input, which I think is true. Yes. Okay. Okay, so for an integer, what we can do is, shoot, I wrote this one already, so I thought it was part of the standard library, but it's not because we defined parse results. So what we can do is write a general function for mapping the type of a parse result when it's okay and leaving the error unchanged. So let's write that. So map result will take an implicit argument and a parse result of type A. So let's write the function. Let's write the function first. So we're going to take a function from A to B and a parse result of type A and turn it into a parse result of type B. So if it's in okay with some value and rest, then that returns okay f of v rest, and errors stay errors. Oh, and we need, all right, I'm just going to make this a type, a general type. Instead of having to worry about whether it's a type with equality everywhere. Okay. All right, so this just then becomes map results. Oops, that's the wrong function. This becomes map bit binary to natural number on parse continued bits of the input. Oops, not the normal map result. Oh, and we need to give it the, there we go. We need to give it the empty list to get it started. All right, so for a literal, we're going to try parsing an integer. And so we can do the same thing here. So map. So this doesn't actually need to be part of the recursion, because this is just going to we're going to try to parse the integer, and if it succeeds, then we're going to take that's the value, that's the natural number. I'm going to turn that into a literal version value of parse integer input. Oops. Okay, that type checked. Good. So parse operator is the one that's a little more complicated, and it has two addressing modes, if I recall correctly. So it's either the total length in bits, okay, so there's 1 bit, and then it tells us either the total length or the number of subpackets to parse. Okay, so we're missing the mode, the length type ID. So if that's 0, then say parse operator by length of it's 1, then we'll parse operator by packets. And drag the version ID along. All right, so now we want to recursively, okay, we're going to, all right, I think this is where we start getting into trouble. So by length, that's okay. We can just take that number of length, give it to another function that says chop off a packet from this and keep going until we've exhausted it. Until we get an error, I think. Although maybe do we need something special to handle end of line? I don't think we do. All right. And by packets, I think we're okay. Let's keep going. All right. I want these to return a list of messages instead. And what we'll do here is the same thing we did above. So we'll take the result of parsing the operands, and that'll give us another parse result. And for 1, it's the same function, parse operator by packets. So we don't have to drag the version around any deeper. All right, so if the length of the input is less than 15, So we want to so the bit length equals bin to nat of did I copy a function? Yeah, first n. First n of 15. So is that including the total length of the sub packet, so not including the header? Uh, 12, 15, 18, 21, 26, 27. I must have dropped 24, 27. Okay. All right, let's just say parse list by length. Hmm. Maybe it was a mistake to separate this out, but sure, let's just keep going. Oh no, these have to be part of this because they're going to recursively call parse packet. Okay. It doesn't feel like we're getting a whole lot done per function, but that's okay. Okay, so we're going to take. Okay, so we need to check the length, make sure it's actually that long. So if the length of input is less than 15 plus bit length, then error. I'm going to parse the list until the end, and we're going to give it sublist starting at 15 and extending for bit length. Okay. So this is the same thing. So parse yeah, so let's make this tail recursive. That's actually a little easier. Okay. All right, so if we reach the end of the input, then return the previous, whatever we've previously parsed. Otherwise, we want to parse packets. So here's our recursive call back to the start of input. So if we get an error, then just pass that error back up the stack. Otherwise, we got a OK and a value and a rest of the list. So we recurse back into this function. And okay, here's where we run into problems, because we don't know that rest is actually smaller than when we started. It should be, but we don't express that in the type. And so in my previous experiments with this, I actually qualified parse result by what was the list that was input, so that we could say, well, the rest is actually a smaller value than that. So what I'm tempted to do here instead is, oops. What I'm tempted to do here instead is just write a utility function that checks that it is in fact smaller, and we return a parse error if it's not. All right, so well, it doesn't even need to be utility error, but we could say if, length rest less than length input, why isn't giving us help about this function? Snock is the eps. Okay. Oh, that's right. It takes a pair. Yuck. Yuck. Okay. Okay, so we append the new message we parsed onto the end and go do it again. And this check tells us that the length has decreased. And otherwise we error out with message parsing did not consume any characters. So it would be a little more, oops. it'll be a little more satisfying if just the type was written so that that was not a problem that could occur. But I guess what I found is that that caused a lot of oh, this is wrong. This is a list packet. List message. Don't know why. Today's error is I keep not putting the name of the list in the arguments here. All right. Okay, could not prove the termination because we didn't actually consume any bits. In this function, we just said, is it 0 or is it non-zero? So there's a way in the tutorial it suggests to handle this. Which is we can where is that? This might even be in the other tutorial. Yeah, so we can do this. So only one of them has to decrease the length, and the other can decrease it. The other can just be an argument. So I find this syntax a little confusing because okay, bar, okay, so this is the value that is decreasing, and so for bar, it's got a 1 at the end, and that can call foo, which is a lower value, but it's not actually I guess it's sort of decreasing, but all right, so we may have to go back and put in length here. I'm not entirely sure. Okay, so this one decreases the length, so we're fine. Oh, these all need to be semicolons though. All right, let's see if that is better. Function's getting long enough, and I'm now worried about I'm going to need to increase the length. All right, so why couldn't... All right, I guess we did need length. I'm not sure why. I think it's because length is because we're not explicitly deconstructing the list in using one of its constructors. We are potentially taking multiple things off with this value. So maybe here instead the length x is less than length L, we could also say and x precedes L in the total ordering. But we'll just leave it with length for now. So we might have to start doing that. All right. Hey, it agreed that our recursive descent parser does terminate. Okay, so that's half of it. The other half is parsed by number of packets. Okay, so we'll do this the same way. We will so this is I think an 11, excuse me. It says 11 bits. All right, so is this right? Okay, so packet list until 0. So packet count. Sublist. Let's do sublist first, count, and then our empty list. All right. And previous list bit. It's a total function that returns a parse results list message. And we play our little trick here again. Let's say, well, we didn't decrease it. We decreased from parse operator by packets to here on the first component, but then when we go from this to the top level again, we're only going to decrease the second component. Okay, so if count is 0, then return the previous, else match. How do we do it here? Yeah, parse packet on the input. So if it's an error, it's still an error. Just copy that whole line. If we're doing this a lot, we'd probably want a helper function of some sort to do it. So parse list until 0 with the rest, with the count decreasing by 1, and till 0. All right. Oh no, this is not right at all. This is not right. We want the suffix after the first 11 bits of the input. Okay, this needs to be okay, and the whole input. Right, so we couldn't do that if we had said that, hey, the parse results always have to strictly decrease the input length. It's, it's not a list bit, it's a list message. All right, so our huge set of mutually recursive functions all work. So the last thing we need to do, the minimum we need to do is write a recursive descent, something to walk the abstract syntax tree and add up all the version IDs. We probably want to print them out, so let's do both. Okay, so I can never remember what I called things. So we're going to print a message. And we kind of, I think, want a indent level. F-star doesn't make things easy because I can't think of an easy way to print just a certain number of spaces. Its printf doesn't even have anything like that, so we're not going to do it. So this is, instead of total, this is going to be the ML effect, which includes everything: throwing exceptions, doing IO, not non-termination, accessing state. It's the top or bottom, just depending on how you think of it, of the post set of possible effects. All right, if it's a literal, then we're going to print string. Say is this how we want to do it? Sure. Okay, so literal version value. Okay. And if it's a operator, version and operands, they want to print the opening. We need a space somewhere in here, I'm pretty sure, or we're gonna be unhappy. Let's put it at the start. Okay, operator and a version number. Okay, and then we're going to use list dot map I, which does something for each element of a list, but just returns unit. And what we're gonna do is use print message itself on the operands, and then we're gonna close the parenthesis. Okay, why is it unhappy here? Oh, it's not map I, it's iter. All right, so let's try some examples. Okay. So we're given a bunch of examples. There's one. Example 2 is that. Wow, we got a lot of examples today. Oops. Copying Windows into Linux. Frequently forget to actually make the copy. So sure, might as well do the other part before we run these. So some versions, and this can be a total function. So version just returns the version. Otherwise, we want to do a fold operation. Okay, we want to do version plus fold. Can using left fold left a lot. Be happier if I remembered which way things went. Okay, so we want to just take total and a message. Yeah, total and a message and return total plus some versions within that message. So I'm going to start with 0 and do that on all the operands. And we made the interactive session unhappy again. Wait for it to catch up, recheck everything, including our big long function. Oh, interesting. This is not a problem I expected to have. So normally in the order that determines termination, all the arguments are ordered below the constructed value, but somehow it's not doing that for the list of messages. So the list itself is in the order, but it should be that the individual elements are ordered. But okay, so this is interesting. I'm going to take a comment and put it in my notes afterwards. So um, uh, all right, and the simple thing to get around this is just mark it as okay. It might run forever. And then we just need to use a non-terminating. Oh, I've run into this before. I don't know. Okay. Oh, okay. It's complaining that if it adds, all right, what was going on there is if we don't give it an argument type, it tries to infer one. It inferred it was an integer. An integer addition doesn't give a natural number, one greater than or equal to 0. But if we told it, hey, this is a nat, and it knows this is a nat, then the result must be a nat as well. Okay. So we just told it, okay, it's fine. It doesn't. Okay, so okay, so I put all the parts together. We want to take list of string. Okay, so take our hex chars, put them all to binary, and then we want to match the parse result. Match. Want to send it to our parser. Probably shouldn't have called that parse packet because it parses the sub messages as well. But parse packet on the input list, and if we get all right, that's kind of silly. We can concatenate the strings. The up arrow is string concatenation. All right, and if it's an OK message, then let's print it. Print message M, and then print a new line, and then so some versions of M. Six examples, I think, yes. 2, 3, 4, 5, 6. All right, so that all type checks. Oh, boy. We did have 7 examples, and I misnumbered them. All right. Copy the make file from yesterday. So this extracts our fstar code to OCaml and then compiles the OCaml and runs it. All right. Well, what did it say about these examples? So V6 2021. Okay. This is an operator with levels 10 and 20. Version 7 with 3 literals, 1, 2, and 3. All right. Version sum 16. All right. So we got a bug here. So we didn't parse that one correctly. And we didn't parse any of the, we didn't parse the one after that correctly too. Okay. So let's focus on those two cases. Just make sure those are the ones. I have to recheck the whole file, so this is not the best way of doing it. All right, this is bugging me, so I'm going to fix it. There's just no good way of dealing with this. Right. So we could put in more details in our error message. It's interesting that we got a So this only found in the second one we only found one of the operators. Did we misinterpret? Okay. All right, let's write a function to print our bits. We have to do this by hand. All right. Okay, so there's the 6 bits of the header. And then this says did we get these right? 0 is length in bits. All right. So this is number of subpackets. And that is 11 bits. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 2. Okay. The first subpacket is 0, 0, 0, 0, 0, 0. Okay. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that is 2, 4, 8, 16. 1, 2, 4, 8, 16, 20, 22. 8, 16, 12, 16, 22. so that is, that's literal. And that's a literal. Okay. Two, three, four, five, six, 7, 8, 9, 10, 11. So literal. Another literal, and then the end. Okay, so we should. Okay, so we could check that we handle each of these smaller cases correctly. All right, let's first fix this error messages. Too short, 0 bits, huh? Okay, so we can't be calling it at the end then. But somewhere in our recursion, all right, we can make these errors recursive. Okay, let's give that a shot. That's very odd. All right, let's check for that. Else if it doesn't seem like it should be the case, but hmm. Decrease the count by 1. We start it with the right value. I'm not seeing why that one should cause us problems, so I wonder if it's the problem that we prematurely truncate here for not returning the right return value in this case. So parse operator by, oh yeah, we're returning the value. Okay, so we need to fix this. So when we parse parse operator by length, so yeah, we return the 0 length list that this gave back. All right, so instead we need to match on it. And so if it's a okay value and rest, then rest is empty. So we're just going to ignore it and we're going to return okay value and suffix. All right. All right, let's try that. That would, I think, explain the other case too. Okay. That doesn't look right though. Yeah, both those are wrong. Okay, that's literal 10. That's literal 11. Yeah, we're still not right. Okay, yeah, we consume length. We consume that first 15 bits and everything else, and only after that do we start reparsing. Okay. I hope it I hope it knows it's that long, at least that long. Should be able to figure that out. All right, that looks better. And the sum of versions is correct. All right, so let's try on. All right, 16, 12, 23, 31. So let's do it on the full. On the full puzzle and see what happens. All right, that's the right answer. Well, today is our programming language exercise, I guess. All right, so I'm just going to copy. All right, so as predicted, our operators are of several different types. Okay, so we got sum, product, minimum, and maximum. Greater than, less than, and equal to. All right, so our parser all right, so let's write a function that given uh, version and the what should we call it? The type ID and the operands returns the message. So one's the product, two are minimum, oh, no, 5, 6. So, if we knew that this value was only 3 bits and that it couldn't be 4, then we could take satisfy all these. So let's actually do that. So we'll say the type ID n is less than or equal to 7 and n is not equal to 4. Okay, so now it can tell that we've exhausted all the possibilities given the constraints we specified. So here, we're going to parse the operator. We're going to give it an extra argument. That's the type ID itself. So that's a number less than 4. We'll add a check for the type ID. If type ID greater than 7, then let's do these in the other order. All right. And so now this message can, instead of calling operator directly, calls operation type with version and type ID and the operands we got from parsing everything else. All right, so that's a pretty minimal change. What did I do here? Okay. So if we wanted to print the message, we'd have to handle all those types. So let's just write the evaluator. So the tutorial might actually help with this problem with the operands. That one of the examples is actually implementing the type lambda calculus. And we really only have to do one application at a time there, so maybe that's not such a good example. All right, so we don't care about the version so much anymore. So we can just blank those out, say we don't care what they are. So it sure be nice if we had all these as functions already. I'm wondering if there's a way to be. All right, so what we can do is we can say if this is exactly one value, then return that. Oh, then return its evaluation. Right. Otherwise, it's a head and a tail. So we're going to val the head and add it to a synthetic message. That's the tail. So we can make the same function do the summing and the multiplication. Just as by pattern matching the whole thing. Okay, minimum. This says it's only got 2 values. Um, so it would be nice if we weren't just returning a natural number, returning an error in case that was ever violated. How can we have min but not max? I'm very confused. Prims. Wow, okay. Uh, I'm flabbergasted. Why does F star have minimum in its standard library but not max? Okay. Okay, this is ML. The ML effect, so we can just do an failure. And the same for maximum. All right. Oh no. That's not guaranteed. It's graded. So we have to do something different. But this is the case for. We'll add the cases for greater than. Oops. Less than. Okay, so those ones do look like these. Okay, so if A equals B, oh no, if eval message A equals eval message B, then 1 else 0. I have all these reversed. There we go. All right, so these work more like the product. All right, so the minimum of exactly one argument. All right, I can see we've got a problem here, but that's the value. The V Similarly, its maximum. So we're gonna better not leave that as product. Okay, we're gonna do evaluate minimum version 0 of the tail. The problem I'm seeing is that we don't have anything to guarantee that we haven't done anything to guarantee that the lists are not empty for maximum and minimum or sub. Uh, I wrote these on the assumption that, maybe the length was 0. So one of the things we could do is specify in the types that these all had to be non-empty lists. And then the type checker would yell at us here. I guess not here. Would yell at us here because we hadn't proven that. And all right, so let's do it that way. Okay, so we're gonna, instead of this, we're gonna say it has to be a list, and we'll make it a non-empty list. Not by calling length, but by calling the cons checker. All right, operands list. Place that by. Well, this isn't a great fit because we only returned a message. So we could switch from using map results to just give it the raw result. Okay, so all right, that's not too bad. Okay, so what we say is we match on operands. So if that's an error, then we return an error. And if it's a value, and we don't. Okay, so operands. We don't care about the rest then. If operands, if length operands 0, then error return an error message. Come on. Else. Okay, so now we gotta make this a parse result. Okay, so we do care. So this is a result. We can do this. We can do this. Just make this one big expression. Rest. Okay. It's not called result. It's called okay. Um. I'm not sure what's going on there. I'm really confused why it's not picking up that this is a message. Oh. All right, we just had to tell it. All right, does this all work? Yes. Does our eval type check? Yes. So all these cases where it's the empty lists are gone, and it can tell that we don't have to deal with those. Okay, we don't have a print message anymore. All right, so what examples did we get? All of them. Those are the same values, aren't they? No, they're not. Interesting. All right, let's try it out. Oh, I rebuilt. I rebuilt part one again by mistake. All right. So it says 354. Our min is wrong. 91001. All right. So our min. That wasn't very good. Because the bug I found was in maximum. Oh, but there we are. All right, let's try that again. Three 54791001. All right, let's try the value we got. Hurrah! All right, well, we started an hour late. Still took us a not inconsiderable amount of time, but finished both parts. So in terms of what we could do better, I like that we're able to sort of put in some structural information here. We could even go further and like say these have to have exactly two. Sorry, these last three have to have exactly two, and make that a parsing error rather than an evaluation error. That would be feasible with a little React. We didn't write new print versions with all the other operators. If we needed to debug further, we could have done that. Um, the best thing for a parser in terms of a specification is to write an unparser and prove that they're inverses of each other. And that could be sort of the spec for this parser. I could prove that. The bug we got is a little tough. We could write lemmas. So let's write one of those lemmas. Uh, so if we've got okay, so if we've got three natural numbers, then what we want to show is that minimum of don't pay attention to the version field of literal 0a, literal 0b, literal 0c. Okay, eval message. Of that abstract syntax tree we created equals the min of A and the min of B and C. So I think we can't, I think it's not gonna just know how to do that automatically. Broke it somehow. I'm thinking not even the normalizer knows that. Oh, this is a problem. Since we wrote it as ML, we can't use lemma to prove things about it. We'd have to write a function with a effect that's at least ML, which is tough because it's the top of the hierarchy. So this is why it's a little nicer in fstar to write total functions, because then you can write lemmas about them. Whereas I think it's possible to do this, but we can't use. It's still possible to do this. We could write a function that had the squash type. Corresponding to our expression. Expected a ghost expression. Huh. So maybe we can't do this. Huh. I think I asked this on a previous day where I ran into the same problem. I don't have an answer for how do we make assertions about things that are not total functions. It seems like it's a good thing for us to be able to do. But I don't think there's an equivalent. So there's where the ML effect is defined. It may be that we could use all and write preconditions and postcon. So it might be that what we could do is we could change this. It's not really the same. So so we could change this function, include a list of preconditions and a list of postconditions. But then the proof would have to be tied up in this function itself. You'd say, if m was a maximum, then the return value had to have certain properties, which is not as nice as doing this. And I don't think, but we want something that doesn't actually execute, which is why it's asking for a ghost type. So I don't know, I may have to ask this on the forum. I mean, so the very best thing I know how to do is go back and fix these types so that they cannot fail. And then this could be a total function. And then we could write the first version and eventually prove it. But I'm not going to do that tonight yet. I'm going to bring the stream to close. Thanks for staying up with me. And took us 3 hours again, but at least I got it done. So good night, happy Advent. I will see you tomorrow.